I wanted to talk with you a little bit today about what we're doing to kind of advance the investments and kind of the technology development aspect for coal technologies. And I think this graph, as I was going through, probably represents to me really our vision for what we'd like to see happen or what we believe can happen. And the graph really depicts the technology path that we believe will result in major reductions in CO2. So I think if our goal is to achieve CO2 emissions reductions quickly and at scale, which is important, I believe, then we feel that financial incentives need to be put in place for a number of different technology options. And I like to point out, we hear a lot about CCUS, carbon capture, utilization, and storage. But I think it's important as we start thinking about these things also to think about high efficiency, low emissions technologies. In Mike's presentation, he talked about materials. When you're operating at these high PSI levels, it's important to have materials that can withstand that heat. So if you don't have that, then having CCUS is not going to work in the model that Mike's talking about. Mike also mentioned supercritical CO2. So the U in CCUS is very important, and we're actually conducting a study for the Secretary now that will be released at the end of this month on utilization. How can we use CO2 in various applications for enhanced oil recovery and the project that Mike talked about, but CO2 can also be used in the creation of fuels and polymers and mineralization and carbonization. So there's a number of different applications that we feel CO2 can be used for. So this is not any one technology operating in a vacuum. I think it's important that we continue to look at a good portfolio. In this chart, you can see the progression at the far left, which is about where we are right now. The average efficiency of coal plants worldwide is at about 33%. Mike was talking about levels up to 50%. Tremendous opportunities to reduce CO2 emissions. 1% increase in plant efficiency reduces CO2 by 2 to 3%. So it's important that we continue to pursue those types of opportunities. And then we believe ultimately carbon capture and storage will bring emissions from coal plants down to near zero levels. So here's what we've been working on with the Secretary over the past year. Last year we released 2 studies for the Secretary, 2 reports for Secretary Moniz, the first in January of 2015 called Fossil Forward. And the key recommendation from this report was really that we have a need for policy parity. Our recommendation was for DOE to take a stronger role in advancing policies and financial incentives that would level the playing field for deploying CCS and these HELE technologies, high efficiency, low emissions technologies. The Secretary liked the recommendation. He actually invited us in to speak with him about what specific recommendations, what specific incentives, what specific policies could be put in place, and I'll refer you to a report that we released in November of last year called Level the Playing Field. And we prepared this for the Secretary at his request in advance of the COP21 meeting in Paris. So he took this with him. I understand that it was used at the Carbon Sequestration Leadership Forum, where policy parity was discussed, maybe less so at the Paris Agreement, but this continues to be a very important aspect and something that I know the Secretary is quite interested in, is trying to get to that level of parity for CCS and HELE technologies. So why parity? As we were preparing those reports for the Secretary, it became apparent to us that it was really to fully appreciate the need for parity, that it was instructive to compare investments for CCS with other energy technologies, other low carbon energy technologies. And in this case, we took a hard look at renewables. Globally, renewables have received about 100 times more investment support than carbon capture and storage to date. When we look at what's happening in here in the United States, we can see that the disparity is also pretty clear. This information is based on Energy Information Administration data. This is not anything that the National Coal Council generated on its own. The Congressional Research Service has also put together some information on this with similar statistics. But we see that in 2013, renewables received over $13 billion in subsidies, while coal received about $1 billion. So about 12 times as much support has been going into the renewable industry. And what we found was these policy incentives and these financial incentives work. And I think proof positive of that is when you start looking at the wind industry. We know from experience that the wind industry has had policies that have been put in place that have significantly driven their technology to scale and quickly. Very short period of time that there has been significant growth. We can see that the potential associated, I think, with having the right incentives and the right policy support in place are actually quite startlingly successful. So I think it can do the same for some of the carbon management technologies that we're discussing here today. What we've seen, we took a look at what DOE has done in terms of supporting demonstration projects for CCS, and really the red bars represented here are the funding that was allocated for demonstration projects for carbon capture and storage projects. Not a lot in the history. There seems to be some consistency, at least in the research and development funding that DOE has appropriated, but we're seeing very little in terms of demonstration project support, and certainly nothing since 2009 has been dedicated to any of the demonstration projects. I think it's also important to note that parity, when we talk about parity, we're not talking about a dollar per dollar match between energy resources. Every technology, every energy resource obviously has a different set of challenges and a different set of benefits. CCS is a very immature technology. It's not yet commercially available. Other energy, low carbon energy technologies such as wind and solar are more mature. So devoting $1 billion in support for very inexpensive mature technologies such as wind and solar is not the same as devoting $1 billion in support for deployment of an expensive immature technology. So we felt that CCS policies, any of the financial or policy incentives going forward, really need to account both for cost factors that relate to the still uncertain technical performance risks. Mike talked about the tremendous challenges just facing just one technology and the big time frame that was going to be needed to kind of advance these technologies. So I think those things are important to kind of keep in mind. So net, we presented the Secretary with a checklist of financial incentives that we felt would kind of bridge this gap on the policy parity area. We talked about some regulatory improvements that we thought would be appropriate, some research and development suggestions, and said, in terms of communication and collaboration, we need to be working internationally with folks to develop some of these technologies, and we need to accept the reality that coal and fossil fuels are going to continue to be a major component of the fuel mix here in the United States as well as internationally, and that it was important to kind of be getting that message out so that we could advance some of these technologies. I have included some kind of bonus slides at the end of my presentation, which I'll just leave, that detail the specifics on the financial incentives and the regulatory policies. So hopefully they'll be shared with the folks in the audience. But both of these reports are up on the NCC website. There's executive summaries if you like the cliff notes. And again, that study that we're doing on CO2 utilization will be released the end of actually August 31st. So look for that. And I'm going to just forward through these slides and get you all set up, Joel, for the next one here. Thank you very much.
Thank you, Sandra. Sorry. Next up, we have Sandra Broekema. She is currently the Manager of Business Development for Great River Energy. She brings more than 20 years of experience in the energy industry, focusing on R&D and new product commercialization in solar, wind, and power generation. Sandra has a bachelor's degree in mechanical engineering from the University of Minnesota Institute of Technology and a master's in business administration from the University of St. Thomas. She holds a professional engineering license in the state of Minnesota. At GRE, Sandra is responsible for business development for Spiritwood Energy Park Association, recruiting additional steam partners for Spiritwood Station, combined heat and power plant in North Dakota, including the most recent development of Dakota Spirit Ag Energy. Great River Energy is a not-for-profit electric cooperative owned by 28 member distribution cooperatives and is a touchstone energy cooperative. Sandra?
Good afternoon. I've been asked to give sort of an industry perspective on the state of the industry, research and development, and what's needed. And Great River Energy is a wholesale generation and transmission cooperative. So we provide wholesale power to our distribution co-ops who serve the end users across greater Minnesota and western Wisconsin. We have peaking plants and wind resources and solar energy throughout Minnesota, but our baseload power plants are located in North Dakota, and they're predominantly fueled by North Dakota lignite. Great River Energy is a very innovative company. We've got about 1,000 employees, and because we have these baseload assets in North Dakota, our engineers are very committed to continuous improvement. And I'd like to kind of walk you through an example of maybe a base hit technology that was developed in collaboration with a number of different entities that have been referenced in the preceding presentations. I'm going to talk to you a little bit about DryFining, which is a fuel enhancement process that really came out of a need at our premier power plant, Coal Creek Station in Underwood, North Dakota. It's about 50 miles north of Bismarck, and it's two 600 megawatt units that were commissioned in 1979 and 1981 respectively. And over 25 plus years of operation, it is a mine mouth plant. Over 25 plus years of operation, the design fuel, North Dakota lignite, at about 6,900 BTUs per pound, had kind of degraded to about 6,200 BTUs per pound. And that caused the power plant all sorts of operational issues. We were maxed out on our mills. So if we had to take a mill out of service for maintenance, we had to derate the power plant. Or we had to do all of our mill maintenance during a scheduled outage with premium labor rates when you're really under the gun to get the plant back up and running as soon as possible, because time is money in that situation. So our power plants engineers got to thinking, sitting around one Friday afternoon, probably in the late 90s. It goes back to 1997, 1998. You know, power plants are very warm places to work. They generate a lot of heat. There's a lot of waste heat in the power plant. The boiler boxes are hot. They're enclosed in buildings because North Dakota is a very cold place, so they need to be protected from the elements. So they were thinking, I'm wondering, question, is there enough waste heat in the power plant to pre-dry the lignite back up to our original design conditions? So that was sort of the thought, the brainstorming thought. So being an innovative company, they got together, they put a team together and got permission to do some testing. They first started with some lignite in a barrel and added heat to it to see if they could drive some moisture off. And those sort of bench scale tests were positive. So they scaled up, and by 2001, 2002, they had applied for a Department of Energy Clean Coal Initiative Phase 1 grant. And they actually were awarded $13 million toward the development of a pilot, a 25 ton per hour unit in the power plant to feed one mill. So they went in partnership with EPRI, and the Lignite Energy Council was on the team to get that application in. They went ahead with that demonstration, and that project turned out so well that our board of directors said, why don't you go ahead and install it full scale on both units, which is pretty amazing considering this is 50% of our base load energy to our members. So it was quite a risk they took, but they had confidence that our engineers had done the homework, they had done the process, we had demonstrated it at 2 tons per hour, at 25 tons per hour, and we're ready to scale up to dryers that were 125 tons per hour, which is sort of the commercial scale unit. We decided to go with a modular unit, not only for shipping constraints, but it gives us a great deal of flexibility. So we've got a total of 8 dryers. They're fluidized bed dryers that are installed that actually use waste heat from the plant. We crush the coal to 6 millimeter minus or 1/4 inch minus so it can properly fluidize and flow through the fluidized bed dryer and then into the combustor and throughout the balance of plant. We were able to improve the energy density to over 7,000 BTUs per pound. So we achieved our design fuel and specification and a little bit more. If you look at, this is a chart from EPRI, which just shows sort of the relative efficiency improvements that are available with various technologies. And power plant engineers typically spend a lot of time and effort trying to get 1/4% or 0.5%. Those are really major improvements in a power plant environment. And with our low temperature fuel drying, the green bar third from the top, we see a little under 5% improvement, which is a huge improvement. And like Janet mentioned, for every % improvement you make, you reduce emissions. In the testing that we did with DryFining, we had an unexpected side effect. Because the fuel is crushed and fluidized and dried, we found out that the heaviest fraction of the fuel dropped out in the front end of the boiler. So we said, hey, this looks different, let's test and see what's in this dense fraction. And it turned out that there was a higher concentration of mercury, which is a heavy element, and periodically bound sulfur. And when sulfur is bound to a pyrite or an iron, it's heavy and it drops out. So this side effect, not only did we get a higher energy density fuel, but it was cleaner. And we set up the dryer so that actually I've got a diagram here that walks through this. I put together sort of a unitized concept diagram to walk you through the process, because there's kind of some recycling and innovation in the cycle itself. So if you've got 100 tons of coal coming in from the upper left-hand corner here, it goes into the coal dryer, and I mentioned we've got about 10 tons that actually drops out before it even gets started in the dryer, because it's the densest, heaviest particles. So if you look at the mass balance around the dryer itself, in the dryer we're driving off 8 tons of water for every 100 tons of coal lignite that's coming in, which if you do the math, you're taking out 18 tons between the water vapor and the segregation material, and winding up with 82 tons of coal product at the end of the dryer. Well, that's actually a lot of energy to throw away, and we believe that there's some viable coal left in the segregated coal that's coming out of the first stage of the dryer. So we decided to put that in an air jig, which is kind of like an inclined hockey table with puffs of air, compressed air, that further classify the material so that the densest materials come out at the bottom, And those are the really heavy concentrations of sulfur, mercury, and ash and rocks and other things you don't want to burn. But we're able to recapture 90% of the material that goes into the air jig and move that back onto the product belt. So overall, we're getting 91 tons of DryFine product fuel out of this process, and we wind up rejecting less than 1 ton or 1% of the material that goes back to the ash ponds because it hasn't been oxidized, it hasn't been combusted, it's no different other than the concentration than the coal feed that's coming in. So that's how the whole DryFining system works. The effects on the power plant, we wind up getting a higher efficiency throughout the entire power plant. Because we've taken the moisture out, a lot of the water out of the fuel, you don't have that water vapor, 8 tons of water vapor that you're pushing throughout the entire balance of plant. So that saves on fan horsepower, the volume of flue gas is less, the exit temperatures are less, the velocities are less, the mill power is less because we're actually crushing less, pulverizing less coal, and the coal that we are pulverizing is much drier and more friable. It's also much smaller because it's been through the dryer. So we're able to see a significant reduction in station service for the power plant. I mentioned that, out the stack, we actually find that we're getting significantly less sulfur, mercury, ash, and the CO2 reduction. So it's a little base hit, but for every ton of CO2 you don't produce, that's less CO2 that you have to treat, essentially capture. And this technology actually can work really well in conjunction with carbon capture and sequestration. We've been in discussion with Sask Power for a number of years because if they do extend carbon capture and sequestration to their additional units, their carbon capture system is 25% smaller because that flue gas isn't coming into the front end of that system. So it's a great synergistic technology there. The results that we've seen at Coal Creek Station, we burn 10% less fuel because of the efficiency improvement. So there's an operating cost savings right there, which is significant. We actually have 54% less SO2, and that's from a combination of mechanisms. We have less fuel going in. We've segregated out those ash minerals, so those aren't going into the boiler to start with. It's a cleaner fuel. Plus, because the scrubber is treating lower velocity flue gas, it's actually more efficient. So if you combine all three of those mechanisms together, it's a 54% less SO2, which means less line, less operating costs for that consumable. We see a 40% less mercury, same kinds of three mechanisms for the mercury. Another unexpected benefit, rarely do you see unexpected benefits, but in this case, we got that very well. We have 32% NOx. Because we were maxed out on all 8 mills, we were using all of the primary air that we had available to run the mills. So we had no room left over in the stoichiometry for secondary overfire air. So we couldn't control NOx that way. Well, we're, instead of all 8 mills now, we're running 6 mills, full load, full capacity at Coal Creek Station. So we freed up 2 mills, which means we freed up almost 17% of the stoichiometry for secondary overfire air. So we've been able to reduce NOx by 32%. We've got about a 4% less CO2, which is small, but it's moving in the right direction. And additionally, we save more than $20 million every year in O&M costs. Most pollution control equipment, you have a capital cost, and then it costs you money every year. So there's never any sort of return on investment for that. It's because it's a mandate. This technology has sort of an equivalent capital cost, but it saves you money every year, so it pays back and it makes a nice economic case for your board of directors. I've been asked to talk a little bit about our commercialization program. Great River Energy is a G&T, We don't sell equipment, but we have taken on a marketing role because the Department of Energy really encouraged us in this clean coal initiative to market and make the technology available, to spread the word. So we've been very active in our trade associations, various conferences all over the world, journal articles. We've received international recognition, and we've partnered with some engineering firms to take this technology forward. And of course, we started focusing on North America, you know, the US and North America, because it would be ideal to have serial number 2 in your backyard so you didn't have to travel so much. But most of the interest we're seeing is from overseas, because overseas is where they're continuing to build new coal-fired power plants. The other thing I want to mention, with DryFining, if you've got the higher quality fuel from the start, the capital investment on a new conventional power plant is 10 to 15% less. So it actually more than pays for the cost of the dryers and the air jigs if you design it in upfront. So that's why there's more overseas appeal at this point, because it actually gives them a competitive advantage going in. In 2010, the first full year of operation, it was an international competition. Power Engineering named DryFining at Coal Creek Station the best coal-fired power plant project of the year, so we're very proud of that award. And certainly if you want more information, there's my contact information. I'd be happy to answer any questions.
Thank you. Next up, we have Brendan Jordan from the Great Plains Institute. Brendan joined the Institute in 2004 and is the Vice President. He has 10 years experience in leading initiatives to promote deployment of clean energy technology. He works across subject areas, including bioenergy, low carbon fuels, transportation, energy, infrastructure, and sustainable communities. Brendan is an experienced facilitator, energy researcher, policy analyst, project manager, communicator, and advocate. He serves as lead staff for the Bioeconomy Coalition of Minnesota, an industry-led partnership working to commercialize bio-based chemical and advanced biofuel technology in Minnesota. He has served for 6 years in a lead facilitation role for advisory groups to the Midwestern Governors Association focused on fuels and transportation, and is currently working with MGA on alternative fuel refueling infrastructure. He is part of the Green Step Cities team at GPI and is working on transportation and land use best practices. He is also part of a team collaborating with Argonne National Laboratories on life cycle accounting methodology for biofuels. He works nationally and regionally on policy to support deployment of low carbon fuels and renewable chemicals. Brendan is part of GPI's infrastructure team and helps support the Institute's work on transmission and the electricity grid. Brendan has a master's in science, science, technology, and environmental policy from the University of Minnesota's Humphrey Institute of Public Affairs, and an undergraduate degree in biology from Carleton College in Northfield. Originally from Eau Claire, Brendan lives in Minneapolis with his wife and 2 daughters. Welcome.
I have to remember to send in a much shorter bio. I didn't know that was going to be read out loud. So really appreciate being invited to speak, and my phone would have to ring right now. Let me turn that off. Thanks a lot to the sponsors and the organizers of this event. I think it's a really crucially important topic, and I'm going to talk a little bit higher level, sort of from a national and even international perspective on why we think these issues are so important. And we come to this from the perspective of being a nonprofit organization, mission-driven. Our mission is transitioning to a low carbon and renewable energy system. And we think that these issues are absolutely critical. And I think highlighting a few of the opportunities we have and why this is sort of a rare opportunity, we have the opportunity to take CO2 and transform it from a waste to a source of revenue. We have the opportunity to increase domestic oil production by 8 billion barrels while reducing CO2 by 4 billion barrels, or 4 billion tons, excuse me. We have the opportunity to do this with a federal incentive that actually would add money on net to the Treasury. We have the opportunity to do this with the full support of parts of the environmental community, coal, oil, labor, and utility sector. How often do you hear international assessment reports that study? These are some of the most peer-reviewed documents in the history of science, and they look at what is it really going to take to avoid going over 2 degrees Celsius of warming. And all of those reports include a large role for carbon capture and storage. There's an International Energy Agency estimate that it will have to be 14% of the solution. CO2 carbon capture is an absolutely essential strategy for sources that you can't manage in another way. Okay, we can take a gasoline car, we can do an electric car instead. Well, you can't do that with, there's a lot of industrial sources where emissions are just inherent to the activity. Steel manufacturing, a lot of industrial activities, there just are going to be emissions. We need to offset them in some way. That's why if we don't have carbon capture and storage, all the mitigation scenarios for climate change are much more expensive because it involves just shutting down important facilities because there's no way to manage the CO2. So every scenario from the IPCC or the IEA concludes that renewables and efficiency alone aren't going to get us to 2 degrees of warming. We need carbon capture and storage. So where does the Midwest and Minnesota fit into all of this? Well, here's the CO2 pipelines. Not a lot of them in the Midwest, none in Minnesota, but hey, there's Weyburn up there. That's a good one. But let's overlay. So this is the activity that's happening right now, and remember, a rationale for doing EOR is it helps us build out the pipeline network. In the future, we might still transport the CO2 from these sources, but it might get injected deeper and just stay there instead of being used to produce more oil. But there's a lot of sources in the Midwest. You've got ethanol plants, which are actually a huge opportunity. We can capture CO2 from ethanol plants very cheaply. It happens to be biogenic CO2 pulled from the air, so you actually get even more CO2 benefit when you do carbon capture from an ethanol plant and store it. But there's power plants, fertilizer plants, natural gas processing, a whole variety of different resources. And over time, there's plans in place to start adding more pipeline corridors if we have a commitment to do more enhanced oil recovery, capture more carbon. So over time, you would start to see the Midwest come into play in a national CO2 pipeline system. And this is based on some actual plans and projections on how you'd bring all these different sources into the mix. So one of the big barriers to doing more enhanced oil recovery is actually availability of CO2, oddly enough. There's a lot of CO2 being produced, but we don't have the infrastructure to bring it in, or we're on the leading edge of technological availability for capture from certain sources. We've been working with a group called the National Enhanced Oil Recovery Initiative that we facilitate to figure out, what federal incentives would help us bring more sources online, what state policies could help, and just to increase awareness of the importance of this strategy as a climate strategy. Really proud of the list of organizations that participate in NEORI, again, including everyone from the Natural Resources Defense Council to Peabody Energy. not groups you always see together, working together, but they are on this issue. Our main goal, our main focus right now is a tax credit called 45Q, which is a tax credit for capturing CO2 from industrial sources and power plants. It is essentially fully subscribed, so we're recommending some changes to increase the availability of this tax credit and also increase the amount to make other sources eligible. There are bills that have been introduced both in the House and Senate that, again, improve the existing tax credit, increase the amount for certain sources, and again, strong bipartisan support. President Obama has also included a carbon capture tax credit for a couple years in his budget. If the 45Q tax credit, according to Senator Heitkamp's bill, passed, over 40 years you'd get 8 billion barrels of new domestic oil, 4 billion tons of CO2 stored that would otherwise be vented into the atmosphere, and you get a deployment of CO2 capture and pipeline infrastructure across the country. Even better, it would pay for itself because we tax oil production in the US. You pay up front, so over in the early years, you're net negative, you're paying to start bringing some of these sources online. Over time, because once you start, you build the pipeline, you start injecting, and you produce oil for a long time from that well. So over time, it's massively net positive from an accounting perspective. So within 10 years, your net benefit is $2 billion. Within 40 years, your net benefit is $100 billion. Your highest net cost in the early years is about $100 million per year. One quick, sort of final point about this. So this is our assessment. This is a terrible chart, I'm sorry, but this is right out of the International Panel on Climate Change. Okay, I'll just point out. This is emissions, annual emissions per year of greenhouse gases, and these are scenarios for where we want to be by 2100. Down here these are the scenarios where the Earth warms about 2 degrees Celsius. Up here are much higher levels. Basically, if we want to get here, we've got to be cutting emissions almost immediately, and we actually have to get to 0 emissions within this century. And emissions right now are increasing. So there's something in a lot of the assessment reports called carbon removal, which says it's not enough to reduce emissions. We're going to have to actively remove CO2 from the atmosphere. Carbon capture and storage gives us a way to actively remove carbon from the atmosphere. And here's how. If we took your alarm cycle power plant, and instead of putting coal into it, some percentage of that coal was biomass, plant material. You were actively pulling carbon out of the atmosphere into a plant, stick it into a power plant, CO2 goes into the ground. You've got a carbon negative, not just a carbon neutral, but a carbon negative power plant. Every international assessment says we need this kind of technology. And so what this helps us with is we're going to overshoot our carbon budget. We're going to emit too much. And then we're going to have to claw it back again. And without having carbon capture technology, we don't have the ability to do that. So this area of technology is absolutely essential from a climate perspective. And I just would like to also add that there's a great chart about the development of wind technology, and I think the important thing to emphasize there is that it took about 40 years to get from, really early scale wind turbines that would have produced power at like $1 a kilowatt hour or more, grossly uncompetitive. And it took a public-private effort, massive government research budget, incentives. Finally, after 40 years, wind power is competitive with other sources of generation. Well, we need that kind of level of investment in these technologies, and we have to acknowledge it's going to take a while. So we need to get started. There's an element of urgency. So on a happy note, I'll conclude.
All right, thank you.